Hi everyone, my name is Snezhana Ilieva and this is a final project presentation for the CSCI E63 course on Big Data Analytics. My topic was TensorFlow and neural network applications in the insurance industry with particular focus on auto, life and P&C insurance. Before jumping to my project, I'd like to first walk you through some of the main concepts of neural networks and where TensorFlow plays in them. Neural networks are the building blocks of today's technological breakthrough in the field of deep data learning. And deep data learning is a subfield of machine learning that is a set of algorithms inspired by the structure of the human brain. And what I mean by this is that much like the human brain, neural networks acquire knowledge from the environment through a learning process. On this slide, you can see the simplest type of a neural network, which has a single layer of weights connecting the input and the output signals. Machine learning, however, can get very complex and very quickly, and deep learning models can become very large. For many models, we'll need distributed training to be able to iterate within reasonable time. And here's where TensorFlow comes to play. So what's TensorFlow? TensorFlow is the first serious implementation of a framework for deep learning backed by both very experienced and very capable team at Google. TensorFlow is an open source software library released in 2015 by Google to make it easier for developers to design, build, and train deep learning models. So as you can see from the picture, the simplest way to explain how TensorFlow works is that it goes through layer by layer, learning information about the pictures, or sounds or handwritten digits, and trying to find out what's the output, in this case, whether it's a dog or a cat. This flow process is called tensor, hence the name for TensorFlow. A little bit more about my project. So I decided to focus on the auto insurance industry and look to understand which of an insurance company's clients are at higher risk of causing a car accident, basing my study on claims data collected in 2013. The data contains information on European motor policyholders, their age, driving experience, policy usage, and vehicle value, among other variables. The technology I use for this analysis, for the data wrangling, and for the statistical analysis is Python. I use TensorFlow for building the neural network and Matplotlib for the data visualization. The insurance data which I'm using comes from Prudential, which is one of the biggest motor insurance in the UK. The final outcome of this analysis would be to determine the probability of a policyholder making a claim during the insurance period, as well as assist the insurance carrier with their pricing and policy optimization. A little bit of background about my project. 7 to 10% of insurance companies' customers cause a car accident every year. Being able to identify some of the key characteristics of clients that are at high risk of causing an accident can not only improve the insurance company's efficiencies, profitability, but also ensure that the insurer maintains solvency and fairness. And in fact, the inspiration for this project came from AXA, which is another large global motor insurance company, which used machine learning earlier this year in a POC example to optimize pricing by predicting large loss traffic accidents. They started by using random forest, which had in their model had about training accuracy of about 58%. They then used TensorFlow and their accuracy increased by 78%. A little bit more information about the data set. As mentioned, it comes from Prudential. It can be found on and downloaded from scansupport.com/help/sample-data. The unzipped and combined data contains 20,477 rows and about 32 features. The dataset contains information from 2013 and includes information on the driver's age, driver's gender, driving license age, policy duration, policy usage, the people who made a claim equal to 10,236 from 20,500 records in total. The technology and software used are Python, scikit-learn, Pandas, Tensorflow, and Matplotlib library. So Python is an interpreted object-oriented high-level programming language with dynamic semantics. It's high-level built in data structures combined with dynamic typing and dynamic binding, make it very attractive for data wrangling, which is what I used it for my project. It can be downloaded from python.org. Scikit-learn is a machine learning library for Python. It can be downloaded from scikit-learn.org/stable/. Pandas is another package which provides very fast, very flexible data structures, which can make the analysis of relational data set very easy and very intuitive. It's Python's building block for doing practical real-world data analysis, and it can be downloaded from pandas.pydata.org/pandas-docs/stable. Matplotlib is the plotting library for Python, which I use for exploring my data and visualizing my training and validation loss and accuracy. Tensorflow, as we mentioned earlier, it's an open source software library for machine learning across a range of tasks. For this analysis, it was used to build and train the model to predict the probability of someone making a claim within the period of insurance, and it can be downloaded from www.tensorflow.org. My hardware environment, it's Windows, version 10 Professional. The core processing unit is 64-bit. Overview of the analysis. So I started by downloading and installing Python version 3.63 through the Anaconda Cloud platform, which is a free open source distribution of the Python programming language for large-scale data processing, predictive analytics, and scientific computing. I then proceeded on to cleaning my data, mapping up my data, unzipping it, formatting it using Python. Once the data was cleaned, I then started to examine my data, examine the features which might have had greatest impact on someone making a claim during the insurance period or not. And for this purpose, I used Matplotlib's library. For the neural network model, I used TensorFlow and plotted the accuracy and calculated the loss and accuracy of the training and validating sets. I visualized the training and validating loss and accuracy of the model with Matplotlib. This is an overview of the neural network model. It contains 30 inputs. It has a learning rate of 0.01. I've chosen 200 epochs of a batch of 16, and as you can see from the slide, on the 200 epoch, the training accuracy reaches about 84%, and the training loss reduces to 34%. This is an overview of some of the preliminary results, which helped me identify some of the features for my analysis. So after cleaning the data, I plotted the data and grouped the data by class, which is my dependent variable, in this case, whether someone will make a claim or not. And the independent variables were gender, policy bonus, policy usage, policy duration. On the first graph, you can see the distributions of age for the claimants and non-claimants, and we can see that the people between 20 and 30 are much more for the claimant population than for the non-claimant population. The driving license age, very similar. We can see that that people who've had less experience are more commonly to be found in the claimants population than in the non-claimants population. Here we see, in the final plot, we can see an overview of policy bonus. And we can see that the distribution of policy bonus is different for the claimant and non-claimant data. Here we can see that policy coverage varies between the claimant and non-claimant data, with people who are covered on the median 2 type policy more likely to submit a claim than those who are not, and with people who are covered on the median 2 type policy coverage more likely to submit a claim than not. In the final one, we can see that the distribution is very similar, and this reflects policy duration throughout 2013 of both claimants and non-claimants. This is a distribution of driver's age. As we can see, the blue line reflects the claimant's population, the orange line reflects the non-claimant's population. We can see that it's slightly higher for the non-claimant's population, the younger the driver is. For the vehicle age, we see a difference again with people whose automobile is younger, is newer, more likely to submit a claim than those whose automobile is older. This is these plots represent driver gender grouped by policy usage and driver gender grouped by vehicle type. As we can see from the first graph, females and males who use their cars on all trips were the ones most likely to submit a claim in 2013. From the second graph, we can see that females who used their cars for no commercial purposes were more likely to submit a claim than females who used their cars for commercial purposes. On the opposite, we can see that males who used their cars for commercial purposes were more likely to submit a claim than those who used their car for tourism purposes. An overview of the final results. For my final analysis, I chose to focus on 15 features of over 30 features included in the original dataset. The model was able to predict if someone is going to make a claim or not by 84% training and validation training accuracy. Training loss decreased from 69% to 34%, and these are just plots demonstrating the validation loss and validation and training accuracy. Lessons learned and future work. Some of the challenges which I experienced was that Tensorflow gave few inconsistent errors. This was apparent when I tried to include car model, which had over 89 categories, and hence this significantly slowed the process of analysis. It took me more than 2-3 hours to process about 200 epochs. The dataset was distributed in several files, and it took me a lot of time to map out the individuals who made a claim to the original database of 20,000 records. The dataset, again, is very small compared to some of the datasets traditionally used with TensorFlow, such as the Iris dataset or the MNIST dataset. Additionally, important variables such as type of claim and policyholder's location address, variables deemed important for price optimization usually, were not included in the dataset due to confidentiality issues, which would have probably impacted the accuracy of the model. For future analysis, having a larger data set and additional metadata, I think could significantly improve the accuracy of the model, and this would in turn allow for greater personalization of the insurance product, improved efficiency and profitability.